Okay, good afternoon, and thank you, Sarika, and thank you to the NetSci community uh, for asking me to talk here. Um, Sarika actually gave me a rather difficult, I don't see her anywhere around, but, oh, there you are. Okay, so she gave me a difficult task. She said, look, we have heard, proper technical talks throughout the day. So in the evening, it should not be so technical, and it should be at least amusing, if nothing else. So I have this with me. What I thought I would do is to largely address everybody not sitting in the first 2-3 rows, talk to the people further behind, and also give you and give the people in the first part of the room some idea of the kind of work that has been going on in India. This morning, Professor Lakshmanan gave a very panoramic view of the nonlinear science community in India, where all it has been, where all it has grown, and so on. And also he summarized a lot of the work that has been going on. I will fill in some gaps here and there. So anyhow, let me start with this apocryphal adaptation of Leo Tolstoy, which I think has been illustrated amply today, that every complex network seems to be complex in its own way. But of course, as you know, this quote is what begins Anna Karenina, and Anna Karenina's story is far too common. So I presume that there will be a theory of complex systems at some point in time. One can only hope so. The fuzzy ball network that you see over there is actually my personal introduction to this idea of network science, which happened in a cafe in Budapest, appropriately enough. And with Janos, the two of us were sharing a coffee or something, I don't know. And we were talking. In those days, we used to work on jamming. Anyhow, so Janos introduced me to the idea of the Erdős number. I don't know, has everybody calculated the Erdős number? All right, Janos is probably 2. Janos is 2. Any other 2s? 3s? 4? 4, there should be a lot. Oh yes, of course, I'm 3. This is exactly, we calculated our Nobel numbers also, and that's what he explained to me. Anyhow, this is Erdős's collaboration network out there, and somewhere over there would be our connection, which makes it 2 or 3 or 4 or whatever, right? And the reason I thought I'd start with that is that Paul Erdős has been in India on several occasions. I'm aware of at least 2, but I recently had an occasion to see some letters that he had written. And for those, I hope you can see, he is writing in 1965, December, from the Center for Advanced Study in Mathematics from Punjab University. He was spending 2 months in India at that time, and he was not working in network theory, although he had done the famous work with Rayleigh already in 59-60, and he was over here. This letter was written to somebody who thought he had proved the Riemann hypothesis. But Erdős was a gentleman, if nothing else. He wrote a long and detailed answer to the person who got this letter, and especially students in India who have all heard of Erdős, we tend to pronounce it Erdos Reni. So anyhow, if you have never seen Erdős's signature, that's what it looks like, and he's the gentleman, always answering. He has visited on other occasions as well, and as Arijit walks in over here, I can show a picture of Paul Erdős at Math Science. He was in Madras visiting the Institute of Mathematical Sciences, and that's him over there. All right. So with this little preamble, and so let me. I mean, the Hungarian connection has been strong, in other words. All right, so I titled my talk very generally as Complexity in the Spotlight, Evolving Networks and Their Dynamics. And as we've seen today, really evolving networks, adaptive networks have taken center stage in many of the presentations. So I'm just underscoring the importance of this area rather than saying something absolutely new, because it also comes with its own set of challenges. All right. The title of the lecture is taken from a review that, actually too many connections, Janos. I mean, this is the JFIS Complexity, is a journal which I was surprised is not sponsoring or not part of the list of sponsors of NetSci-X, because they certainly are involved in NetSci. JFIS Complexity has a large editorial board, of which at least 3 or 4 of us are over here. And right after the 2021 Nobel Prize in Physics to Hasselmann, Manabe, and Parisi, Ginestra Bianconi, who was the editor-in-chief, she suggested to us that we should write some kind of an editorial on what is the importance of this Nobel Prize, because as this community has a very strong overlap with the community that recognizes that the Nobel Prize was given to them. So this was a Nobel Prize for complex systems, this was a Nobel Prize for complexity, chaos, all sorts of things. But I think it was a good idea to try to take stock. And one of the nice things that happened is that one could see what was of interest to people across the world. The editorial board has people from all over, India, Europe, North America, South America, China, Japan, and so on. And there was sort of an amazing confluence of opinion, also different kinds of emphases that went on. And the reason I thought I would bring it up over here is that a lot of what was said in the context of complex systems really does apply to complex networks. The collective view was really to emphasize a number of aspects of complex dynamics and complex networks. And these are areas that, at least when the meeting is held in India, as you saw today, many of the people who are initially at least getting into the area of complex networks come from a nonlinear dynamics or complex dynamics background. Right. Now, I'm going to quote extensively from this particular editorial, and I would warmly recommend, particularly to the students or those who are getting into the field, those who are maturing in the field, that this is worthwhile to see the opinions of various different people. And I will just quote from them and try to emphasize their importance in the area of networks. So one of the main things about a Nobel Prize is that it makes you think about why a prize is given to a field and what is its utility. So the idea is that complexity science can actually address some of the most pressing problems and pressing challenges that humanity faces. And, it's not as if we need to emphasize, we don't no longer need a world war to show that all of humanity is linked. Every day in 100 different ways, we are made deeply aware of this fact that what happens in one part of the world has a significant impact in the other parts. So Ginestra, in her editorial, was sort of being discursive and was expanding on what are the areas. So she's, some of these may seem like no-brainers, but they also need to be said. The problem of climate change requires combining all sorts of interdisciplinary approaches to tackle the challenges posed by rising temperatures to climate, to the environment, and to the ecosystems in the near future. It's also important from the point of view of social sciences, because how human society is going to respond to climate change is going to be a cooperative phenomenon. I mean it in the cooperative social phenomenon sense. We cannot do things in one country to mitigate the effects of climate change if neighboring countries don't do similar things. Those of you who have had the distinct displeasure of traveling through Delhi will know that in the winter months, Delhi is it's unbearably polluted. A large part of the pollution comes from burning of agricultural waste. But this agricultural waste is blown from the west part of India over onto Delhi. There's very little agriculture that goes on in Delhi. It's an urban center. But also this agricultural waste is burnt in neighboring countries. So a lot of stuff that happens in Pakistan is cross-border. So we have a lot of, we need to cooperate on matters like climate change if we are to solve something in a substantial way. COVID told us that nobody is isolated in this world, that essentially everybody in this room is aware, has either had COVID or knows somebody who has had COVID, and regrettably, many of us also know those who have died from COVID. At the height of the pandemic, I sat and I wrote a blog which said we have 1 degree of separation, maximum, right? So from anybody. So this is a pandemic that affected us all. So we need to understand that, how to predict the evolution of large pandemics, because well, inside India, we were aware of a severe and drastic policy failure. We had no great idea of what to do, and it also exposed some of the flaws in our data collection methodologies. There was very little true and accurate information that went through. So again, this is an area where complexity science can inform policymakers. And we know that pandemics spread through the airline network. And the airline network is going to expand even more as airlines merge and become larger than whenever, right? So we need to understand what social mobility is, how people move. In India, a large number of cases were spread by people walking home because everything was shut down. People had to walk large distances to get to where they had a place to stay. And along the way, we found spreads of COVID. Now, another area, and I'm just going to list, these are all Ginestra's writings, but I don't disagree with them, and I don't think anybody else does. But one of the areas where complexity science can say something will be to make advances in precision medicine. Now, this has been an ongoing dream for a very long time, that you could walk into a doctor's chambers and be told something that would solve all your problems. The complexity challenge really is to use network science, machine learning, AI, along with the more difficult ones, molecular biology and neuroscience. Right? So, I mean, you can have precise data. Anybody who's looked at biological data knows that to first approximation, at least, it is, I mean, the precision is not what characterizes it. Now, most diseases are complex, and it's important to embrace the complexity and heterogeneity of interacting networks of the cell, and we've seen some examples of that today. She also went on to talk about brain function as being one of the big challenges of complexity, and again, like I said, that is a no-brainer. So in the past few years, we've given a lot of prominence to the study of complex systems, the study of networks, not just because of the prizes that was being done even before that, but these are of crucial importance to diverse communities. And the network itself is not nearly as interesting as what it either represents and the dynamics on it. So two networks that look very similar may really refer to very different kinds of processes. You've got social networks, epidemics, and so on. Now, the complexity that we see in networks, again, we've seen how this goes. It comes from an interplay of randomness and order, both in the dynamics as well as in the interactions of the various elements. Now, we've seen that even highly nonlinear systems can be frequently approximated, and we saw that in a talk this afternoon, approximated by linear sets of equations. But how does this play out on the network? If we are going to address the big challenges in coming years, we really need to understand temporal networks, time variable networks in a much, much better way. This is not to say that there are not already some impressive achievements, but I think we understand the nature of feedback and modification of networks not as well as we should be, as we should. All right. Now, what I'm going to also try to give you a flavor of is the kind of work that has been going on over here. So one of the earliest phenomena that was studied in the area of networks was to look at the coupled dynamical systems. And shortly after, Pecora and Carroll and others brought the whole problems of synchronization to the attention of the community, the nonlinear dynamics community. There were some of us who went on into looking as to how this would play out in network systems. So one early work, which is with, the person who led the study was Prashant Gade, who is now a professor at Nagpur University, and a student of Amritkar who is in the audience over here. So in this work, what we did was to look at just very simple dynamical systems, coupled logistic maps, and these coupled logistic maps, we looked at them on a Cayley tree, perfect branching, simple one. This is, the work is 1995. I know, people can look at this network and, say, well, this is a kiddie, it's a toy version, but okay, it was 20 years ago. 30 years ago. Okay, so for 30 years, it's okay, all right? Now, the important point over here was that we were looking at regular networks without loops. And we wanted to understand something about the process of synchronization. And we found, not surprisingly, that global synchronization happens, cluster synchronization happens, clusters over here being all the nodes at the same generation. So then there was a generation gap in the sense that all the nodes at one generation were synchronized and different from those in another generation, and so on and so forth. And there were different and interesting spatio-temporal patterns. Now, Gade went on to work on other problems. But you know, he comes from the group of Amritkar and Sarika, who I just want to remind them of a paper that they wrote in 2004. This was presented at a conference in Madras, in Chennai, sorry, on perspectives in nonlinear dynamics. It was a satellite meeting to StatFizz, emphasizing the connections between the network community. There was some really amazing stuff that was done in this particular work, which was a precursor of many other discoveries that have gone on. And it was also, it's just a small part of the work that Amritkar, Pandit, Sarika, let me be proper and say surnames, so Jalan, Gade, and others have done. Their results on cluster synchronization as well as time-dependent networks, what they called floating nodes, nodes that moved in and out of clusters, it was an original observation at that time. Gade himself studied not only the Cayley tree that you saw over there, but he studied some other random networks as well. And he showed that the graph Laplacian, we've already seen that on the screen many times today, the eigenvalue spectrum of the graph Laplacian is what is the important determining factor between coupling constants and synchronization. Not so surprising today, but like I said, these results are actually among the earliest that happened in this area. Related considerations have to do with self-organized criticality. One of the important things about complex networks, and people are talking about this in current times, is the so-called sandpile group. The sandpile group of a complex network is defined by having a sandpile, which let me just very briefly tell you. This is a discrete cellular automaton. At every node of the network, there are a number of grains, integer number of grains of sand. And if the number of grains of sand on a network is equal to or greater than the degree of that particular node, then that node topples, and one grain each is sent to its neighbors. Right? This is this is just the network analogy of the Bach-Tang and Wiesenfeld self-organized criticality model, and I've already seen that on the screen at least one talk today. So this is not an unknown thing. But the sandpile group is something that was actually presented in the community by Deepak Dhar. And he showed that these sandpiles have the so-called abelian property. Namely, if you have a sandpile with this kind of rule, then it really doesn't matter. The order at which you add sand doesn't matter. Okay? So now, why is the sandpile group important? The sandpile group is actually it's related to the graph Laplacian. It's called it is termed the Jacobian. It's a critical group, and this mathematical terminology I don't fully understand. It's called the Picard group of the graph, and so on. And it's also related to the number of spanning trees of the network. So the connection between the type of network and putting a self-organized critical system on the network, that seems to be a very deep connection. And there is no result for me to present over here, but I'm just posing the question. If you have a network that is evolving, how does the group evolve? We've already seen in the previous talk, there was a result where you put out one particular node and the centrality moves to another area and so on. We are aware of how networks evolve, but I'm just suggesting that if we analyze it in terms of quantities like this, it might be a fresh characterizer and something quite interesting to see how networks actually evolve. Right. Now, complexity science can also address pressing challenges in terms of impact to society. So the idea of using it for precision medicine is extremely important. And here, one of the diseases that mankind has been seriously looking, there is progress as we go along, but mankind has been looking for solutions to the problem of cancer. Now, cancer is a systemic disease rather than something that is caused by a single gene. And again, like susceptibility to COVID, people do have an individual response to it. We don't understand exactly why two people with exactly the same genes and exactly the same environment, so the same nature, the same nurture, but very different consequences of cancer. So when you look at the data for cancers, it's known that there are some genes that are extremely important, and one of them is a gene called P53, and this seems to occupy what would be a hub, a very central position in the molecular biology of almost all cancers. And a lot is known about the network structure, where it is, what it occupies, who it affects. There's a lot of biochemical terminology which I'm just not going to get into. But the idea that the P53 network could be a scale-free network was already mooted in the year 2000. The three authors of this particular review or News and Views feature in Nature were the people who discovered the molecule. All hardcore biologists, and yet the language says, as when a highly connected node in the internet breaks down, the disruption of P53 has severe consequences. Or when it is put out, or what was the attack? There is no plan B over here, by the way. All right. Once P53 is put out, that's the end of, well, it's not the end of the person, but I'm saying that, the network is gone. All right. But there are, and this is something that molecular biologists have spent a lot of time thinking about, there are a variety of interactions within the cell. If you take any DNA and spread it out, that gives you the genome. And the genome is expressed as a number of proteins, giving us the proteome. Now, the proteins interact among themselves, so they are, obviously, they have function and they interact among themselves, but they also go back and interact with the DNA. And one can immediately see that you need to have a bilayer description of this kind of system, except that it's not a bilayer, it's a trilayer. These proteins are now going to affect the metabolic network. They affect the metabolism of the organism and so on. Right. So at some point, Janos, tell me. So one of the works that, one realization that you have this bilayer network is some work that we had done, I don't know, some 10, 12 years ago. You identify a bunch of disease-specific genes in breast cancer. Using microarray data, you look at correlation matrices, and you try to figure out what those faint lines are just telling you, how they are, whether they are linked to each other or not, what that particular network is. And this network can be analyzed in terms of modules, looking at those that are interacting more closely with one another as opposed to others. I mean, these are all language that we have been hearing today. But then the interesting thing is to see what are the proteins that these genes express. And these proteins are just the image of this particular network until you start looking at the protein network themselves and see what are the communities that they are interacting with. Right? So the final network is actually this bilayer system where you have genetic data in the bottom layer, protein data in the upper layer. Now, this is what actually happens because the genes interact with the proteins come back and interact with the genes, but the proteins interact with more proteins. So this is just the kind of complexity that we deal with. Now, when you finally want to target a particular cancer, many times it is easier to target proteins rather than to target the genes themselves. So you kill the messenger. So when you're trying to do that, you try to identify submodules, important submodules, and put out these submodules so that you can quell the cancer. This is what precision medicine is. And in the best case scenario, one can identify new candidate targets. You can sort of find a particular gene just through data analysis and discovery. But this is unusual and rare. This is because genes or protein networks give you a static image of the connectivity and relatedness of components. Network coupling, network topology, the effect of that on the dynamics can be quite considerable because in this, as in everything else in life, timing is important. So you may have a network, but you're just delivering the product that you need, it's gone. And the network itself evolves due to complex biochemical rules, epigenetic rules, and so on. So interactions are both time and context dependent. Right. Now, one kind of network that combines both social and technological features are public transportation networks. To ask the obvious question, why are the California fires quite so devastating? It's tragic what is happening right now, there's this entire community in Altadena, Pasadena, where Caltech is situated, which has essentially been wiped out. Not Caltech itself, but a little further to the north. I was made aware of a rather interesting feature of this, and that is that most wildfires in California are related to power generation, transmission, and distribution. According to the data from the US Forest Service, this is reliable data. So some of the most destructive fires have been traced back to problems with utility poles and fire lines. Now, fire lines are moving, the utility poles and the power lines are moving across where people live. So it's almost a given that they're going to have a maximum impact on the social network of people. To add to this, the lack of rain for the last year, the wind every day today, that is both the climate and the weather network. This affects now the technological network, the static network on the ground. You've got this mobile network which is moving around, and this is what is making this problem extremely, this is such a problem for everybody that, I don't know whether the next APS meeting is going to be in LA or not. It has impact. Well, I thought I would share with you, one of the evolving networks. This is not a temporal network. This is just a network that has evolved in time. All of us are familiar with the railway network of India. If you're an Indian, chances are you have traveled extensively on it. If you are not an Indian, you should try it. But no, seriously, you should try it. I'll take out insurance on you first, but okay. So what I'm going to show you is an image of the railway network in India that evolved from the year 1870 onwards. So in 1870, there were actually very few lines. What you see over there are all the lines that were there in India, all right? And many of us are not aware of it, and I got interested in it for completely different reasons. And what you can see over here is really, where do people live? All right, in 1870, the population of India was somewhere about 200 million, maybe less, all right? So there were lines that were connecting some places of habitation, ports, mines. The British were very keen on transporting whatever they could to the seaside and ship it to England. I'm talking about the history of India, Janos. All right. By 1911, which is the picture that you see over there, the network had actually improved and increased rather significantly. The different colors are for different companies. At one point in time, it was not just one Indian railway system, there were many railway systems. And what you can see over there is really the extent of it. Again, what the picture tells you, if you are willing to sit and analyze it, is really where are the people, where are the natural resources, because this was a network that was exploiting the subcontinent. By 1942, that's the network over here, you can see that it had expanded even more. But still, there were large parts of India that were simply not covered. The British didn't feel the need to build a railway where it was not going to be lucrative. And what you see over there is what the network is today. And you can see that a lot of the blank parts of this screen have been filled in over there, because there is a social responsibility to build your networks, build your transportation, to let people go wherever they need to. So the network over here is actually providing you an insight into history, all right, which is a little different spin from, we've seen that networks tell you about societies and so on and so forth, but here the time evolving network, even though it's a static network and all these snapshots, tells us more. And one of the very early works that looked at this network was by statistical physicist Parangama Sen, and the last name Manna, you all will recognize working on sand piles. So the main conclusion was that the Indian railway network was disassociative, which is not surprising because there is this combination of social and technological networks. People are building these networks to speed up transportation and communication with each other, so chances are that this is how it would be. This interplay of social and technological, necessitates the study of evolving networks. Also in Kolkata in 2005, there was an important conference that seeded a lot of activity over here, and there are many people in the audience who were there at that time, but it was a very, very useful conference for sparking a lot of work. I've already pointed out Amritkar and Jalan did a lot of work, and I will have a chance to talk a little, if I may, on some of the other work that came out of it. So let me start by quoting Anthelme Brillat-Savarin, who said, "Tell me what you eat and I'll tell you what you are." So one of the more interesting outcomes of network science in India has been the development of food as a complex system. So this is a study by Ganesh Bagla, who was one of the people there in the networks conference. It took him 15 years to do this, but he looked at culinary creativity by making food, well, I don't always agree with the terminology, but this is an interesting kind of study where he looked at the kind of ingredients that go into common foods every day and how does one mix and match them in order to make food that tastes good. Having a lot of very nutritious stuff is not, I mean, it's not the end of the story, because you've got to look at cultural preferences, social preferences, religious preferences, and so on and so forth. This study is to try to look at all the kinds of ingredients that you use, what are all the things that are available. There's no point having a wonderful recipe for truffles if truffles don't grow in India. And you get the idea, right? So we need some sort of geographical and cultural context. So this is a sort of an interesting approach that Bagler has been doing, including throwing up new recipes just based on proper combinations. I mean, okay, this may not be the most significant kind of application of network science, but this tells you also that you could use network science for social benefits, because now you have a structured repository of recipes, and you have consequences for food security, because we are actually dependent on 4 cereals and 3 types of meat. Beef, chicken, fish, that's it, and rice, wheat, and so on. Okay, so the food security situation is actually somewhat grim. And again, to quote Bria Savana, the discovery of a new dish does more for the happiness of the human race than the discovery of a star. Okay. I will just mention, because I do need to, the work on adaptive networks also started in India very early. And this was by Sanjay Jain and Sandeep Krishna. They looked at autocatalytic sets and the growth of complexity in an evolutionary model. So this was basically to look at large sets of coupled chemical reactions, just linear equations, right? And then at a certain point, when a steady state was reached, you remove the species with the least concentration and replace it by a completely new species. And you keep doing this and doing this until suddenly you have an explosive growth. So there is a phase transition that happens in such systems, and they were able to show that what basically happens is that you have an autocatalytic loop. So you start with a plain network with no loops in it, and then suddenly you just keep evolving, and boom, you have a appearance of a loop, and then you have a change in the quality of the system, right? Now they've extended this model to address number of problems, keystone species, evolution and innovation, and so on and so forth. And there's been some very nice reviews recently of adaptive dynamical systems, which have been talked about over here today, but networks that keep changing their appearance as time goes on. In the very last minute, let me just point out that there are many open problems, and I really hope that the next time NetSci comes to India, that students over here, I mean, we will see a fresh lot of people looking at a variety of problems, looking at many of trying to classify complexity. There have already been some issues on that. There have been how to go beyond pairwise interaction. Maybe fundamental interactions are not always pairwise, it's just our approximations that do it. And one of the most important, how does one deal with data complexity? These are all opinions from different people in the editorial, so I'm just summarizing. The connection between data science and complexity science is something that needs to be explored. How to combine these with artificial intelligence, I already know that a lot of people are doing that. And so with that, let me just thank you.
Thank you, Ram, for this broad and entertaining overview. Are you taking questions? Yes, please.
Doesn't seem to be a need, but anyway. And it was supposed to amuse.
Okay. There is an announcement. Thank you, Ram.
So we invite you all to the informal mixture, which will start in JBR Hall at 6. It will be led by Professor Barabasi and Professor Sanjay Puri. There are free snacks and drinks, but the beer is paid. And the another announcement is that the people who have their posters today, please go to their posters so that the panel can judge your posters. Thank you.